Uh, Today's topic of discussion is outlier detection in a set of data. As I say, as I have discussed in my previous lecture, that the second step of model development is outlier detection. Actually, not second step. If I say that like this, first step, let us recapitulate what we have learned in the previous tutorial. First step is data collection. Second step is trend detection. Data collection, trend detection by runs test, or there is many other methods of trend detection. And in the third step, which is the prerequisite of the model development stage, it is the outlier detection. From the fourth step will be the model development. So, what is outlier? Outlier is, outlier is the abnormal, extreme, uncommon data points among a set of data. So, if your data is varying from 10 to 50, then in your data there might be some data points which is like 5 or which is like 70. Such data points is known as outliers. Suppose for take an example of rainfall of the last 12 years in say the state of Tripura. So you will find that 50, 70, 120, 150, then 180, 200, 200, 210, and suddenly it is very low, 20, 15, then 30, then 10. So if you can see, more or less the rainfall varies within 50 to 200, correct? But sometimes it has gone beyond 200 and also it has gone beyond 50. So those values are actually exceptional values in our data set, which doesn't goes with the trend. Some abnormal value or extreme values. So the method which helps us to detect such exceptional values is known as outlier detection method. And why we detect these outliers? Because inclusion of outliers in your data, which will be used for model development, will make your model erroneous. Because if there is example, that means the data where the trend is there, these data with exception, which is also known as noise in some cases, then this trend will become hazy. Because during trend analysis, they will consider both the example data along with the exceptional data, the noise data. So, as a prerequisite to the model development state, we must detect the noises of our data and delete them. One of the methods for that is outlier detection. By outlier detection, we detect the noises and try to delete. So there are many different methods of outliers. You see the significance is written here. So significance of outlier detection methods. which is detection of extreme data, which are found to be not matching with the trend of the sample population, either over or under mean value. That means either very over and very under mean value. These are the exceptions. And as I was explaining earlier, various methods are available. And this is new. Selection of methods is based on sample size and underlying distribution function. Every data set has a distribution function, and based on the distribution function, we select the method. But first, the number of data in the sample size is considered for selecting the. So here in this slide, you will understand what I was talking about. Size of sample data, if greater than 25, then apply Rosner. If less than 25, apply Dixon Thompson. Any number of data, the Chauvenet method is able to detect outlier problem. But Rosner method can only be used when number of data points in a sample data is greater than 25. And Dixon Thompson method can only be used when number of data points is less than 25. This is the restrictions. But in case of Chauvenet method, you can use it when there is 100 number of data or when there is 20 number of data. In any size of data, Chauvenet method can be used. So another thing I had said that the inherent distribution of the sample data is also considered. You see, maximum cases, sample data follows a normal distribution pattern, but in some cases it also follows other distribution pattern. But these are not the objective of our discussion in this presentation. So let us go for the next one, that is the how Chauvenet method is utilized for detecting outlier. So here first step you have to calculate Z, and how it is calculated. X is the data of your sample data minus mean of your sample data divided by standard deviation of your sample data. So what I am saying as sample data, actually I am referring to your number of data you have collected, the set of data you have collected. So there might be 10 number of data points, there might be 100 number of data points, there might be 500 number of data points. But set of data that you have collected is the sample data. So you have to calculate the mean of that sample data and standard deviation of that sample data, and you deduct the mean from each of the data and divide the result by standard deviation to find set. So for example, if this is the data 50, 70, if this is the data point, then find the mean value of this data, sigma value of data, sigma means standard deviation, and then you deduct to find the Z of the first value, that means 50. You calculate, you use this formula like this, 50 minus mean divided by standard deviation. Similarly, for calculating the Z75, the second data point, second, this is what you call. And similarly for all the data points, here number of data points is 3 plus 4, 7. So 7 Z values can be calculated. And then you have to identify what is the critical value of Z from the table of distribution of the sample data. This table is shown like here. So how to? So You have to identify the critical value of Z, which is, you can find it from the normal distribution table for finding the critical value of Z. So, how to find the critical value of Z? If n is your number of uh, sample size, number of data points, for the example that I am showing here, 7 number of data points is there. Then n will be 7, n will be equals to 7. Then you inverse it 1 by 2n. So it will be 1 by 2n means 1 by 2 into 7, that is 1 by 14, which will be equals to 0.0714. Now all these values, as I have indicated already, in this table, this table is known as normal distribution table for finding the critical value. So these are all 1 by 2x. Now you identify your own 1 by 2n, that is 0.0714. But it seems that this table is starting, the starting 1 by 2n is 0.5. So as this 0.0714 is less than 0.5, we will assume that the critical value of Z is 0. However, if your 1 by 2n is this one, suppose for some cases, for some example, you find that your 1 by 2n is 0.7324. Then how to calculate the critical value of Z? Now try to find the row heading. This is, you see, 0.6, and the column heading of your 1 by 2n. This is your 1 by 2n. So 0.02 is your one column heading, and 0.6 is your row heading. So add row heading and column heading, it comes as 0.62. So for that case, the critical value of Z will be 0.62. And if the calculated Z values of your sample data is more than the critical value of Z that we have calculated from that table, then that data is a outlier. So for our case, for our example, what we find is critical value of Z is 0. And suppose this Z50 is, for example, after applying this one, this formula, or this formula, the same, all are same, it is found to be 0.15 or something like that, then Z50 will become outlier. But if I see that if the Z50 is found to be minus 0.15 or less, something, some value which is less than 0, then that point is not an outlier. So to be an outlier, the Z of your data point must be greater than the Z of the critical value, or critical value of Z. Now this, the weakness of this method is Chauvenet method can identify only one outlier. Once it has detected an outlier, then it is useless to apply this method. So that is why what are the steps you have to follow for Chauvenet method? First, your sample data is collected. Then you have to find the critical value of Z from that normal distribution table that I have shown you. And for identifying critical value of Z, you have to calculate 1 by 2n, where n is the total number of data points or sample size. And all these values are 1 by 2n's. So suppose this is your 1 by 2n for your case. Then look for the column heading and the row heading and add both. That means you will add row heading with the column heading to find the critical value of Z. So any of the Z value calculated for your data like Z50, Z75, Z100. If it is greater than this critical value of Z, then that data is an outlier, otherwise. So this is in summary what is Chauvenet method. Now come to the Dixon Thompson method. So how this is done for Dixon Thompson method? First thing you must uh, observe that Dixon Thompson method can only be utilized when the total number of data point or the data size is less than 25. Then only you can use this method. So the first step will be to arrange the data in ascending order. So the first step is to arrange the data in ascending order. Ascending order means from lowest value to highest value, or the smallest value to largest value. This is the first step. Second step is smallest is ranked first and largest is ranked last. Okay. Then we have to determine R. So how it will be determined? Here also you will use a table. This is the table. So in this test you can detect low outlier, that means small minimum value outlier as well as maximum value outlier. If you want to identify the maximum value of outlier, then to find R, you have to use these formulas. If you want to identify the lower value of outlier, that means the minimum value of outlier. But if you want to use the maximum value of outlier, you have to use this formula. So which formula to use when? When your sample size is 3 to 7, you will use this formula. When your sample size is 8 to 10, you will use this formula. When it is 11 to 13, when it is 14 to 25, greater than 25, you cannot use this method. So let us now look into the formula, what it states. So take, for example, for our case, sample size is 7. If you consider this example, correct? So our case, sample size is 7. So we will use 3 to 7. So we will use this formula. Suppose we want to detect the minimum value outlier. So minimum value outlier is, as the data is arranged in ascending manner, so the first value or the value with rank 1, 2, 3 like this will be the minimum value outlier. And the largest value will be in the bottom of the data set. So higher the rank, higher will be the value of the data, as we have arranged the data from small to large. Okay. So to detect the smaller value outliers or low outlier, how to calculate R? You see, I will just write it again. R x2 minus x1 xn minus x1. x2 means the second data point of the data you have arranged from smaller to larger values. Then x1 is the first value of your data, that is the smallest value of your data. xn is the largest value of your data, the nth value of the data. If you have 7 number of data, then xn is the 7th data point, the last data point, because you have arranged your data point from the smallest value to largest value. So x1 becomes the smallest value and x2 becomes the second smallest value and xn becomes the largest value. So if you use this formula x2 minus x1 by xn minus x1, then you will find the R. Okay. Next, so you have calculated your value of R for your data set. Now now you have to find the critical value of R. Here also that in case of Chauvenet it was critical value of Z. In case of Dixon Thompson it is the critical value of R. So here also you will use this table, this part, and this M is the number of sample size. So as we have 7 number of data, our sample size is M is equal to 7. We are using this data, the same data example that we have taken for Chauvenet method. 7 number of data points is there. So our M is equal to 7. Now this one is this 5%, 2.5% and 1% indicates error or level of significance. So 5% error means 95% accuracy. 2.5% error means 97.5% accuracy. And 1% error means 99% accuracy. So according to the desired accuracy level, you can select the column. Suppose we want to select the most accurate one, that is the 1% level of significance. So then what we will do to find the critical value of R, you see for the data set of 7 data, that means sample size of 7, level of significance 1, this is your critical value of R. This is the critical value, RC. And the condition is that to be an outlier, so to be an outlier, this critical value of R must be less than your R. Okay, in this case, Chauvenet method, your Z or the Z of the data points, whenever it is greater than the critical value of Z, that data becomes outlier. Here also, in case of Dixon Thompson method also, when R of your data points become greater than critical value of R, that data RD becomes an outlier. You understand what I want to say? So in summary, if I summarize this thing, Dixon Thompson method, if I want to summarize this, first, when you find the data series, when you have completed your data collection, what you will do, you will arrange the data from smallest value to largest value. That means in the ascending order. You will assign the first rank to the smallest value and the last rank to the largest value. Then you will try to find the R. So how you can find the R? If you will use this table. If you are trying to find the outlier in the minimum value, that is the smallest outlier you want to identify, then you will use this formula for calculating R. And this formula is nothing but this x2 minus x1 by xn minus x1, where x2 is the second smallest value, but the second rank data, and x1 is the first rank data. This is the smallest value of within the data set, and xn is the largest value within the data set, and x1 again is the smallest value within the data set. So when you have found it out, you have to find the critical value of R. So based on the significance you want, level of significance you want, and your sample size, you will find the critical value of R. Here we want that there must be 1% level of significance, and our sample size example data is 7. So RC will be 0.620. So if x1 in your data is an outlier, then R will be greater than RC. If this is the case, then x1 of your data or the lowest value of your data is an outlier. Similarly, if you want to use the high outlier, you have to detect the largest outlier. Then you have to use this value, which is actually R is equal to xn minus 1, xn minus x1. So what is that? Xn is the largest value, xn minus 1 is the second largest value, xn is the largest value, x1 is the smallest value. Because we have arranged the data points into ascending order of magnitude, so the smallest value lies in first and largest value lies in the last. That's why n is the indicates last value. N minus 1 indicates the last, not the last value, just before the last value. So in this way, this will be the largest value, this is the second largest value, this is the largest value, and this will be your smallest value. X1 is smallest value. So when you detect this, your R is determined. Now you have to find the RC. So if you want a level of significance of around 1%, your sample size is 7 in our example case. So this will be your RC, critical RC. So when your R is greater than critical RC, then that will be a. So this is what the condition is. This is what the condition is, and to find outliers with the help of Dixon Thompson method. Besides this Dixon Thompson method and Chauvenet method, there is many other methods that I have mentioned here. Z-score, probabilistic and statistical modeling, linear LRMs, PBMs, and information theory models. You can click this link to find the details about those methods, but they are not very widely used. So mostly Dixon Thompson, Chauvenet, and Rosner's is used. I will discuss about Rosner's in some other video, other lecture. And for now, I close this lecture up to this point. Thank you for your patience.